Good afternoon, everyone, and welcome back. We'll continue with the graph theory sessions now. Yesterday, we saw the basics of graph constructions and obtaining graph parameters in Sage. We also saw some very basic graph operations like disjoint union, join, Cartesian product, lexicographic or Kronecker or direct product, right? Tensor product. So today we'll look at matrices related to graphs. Right? The common ones are adjacency matrix, Laplacian matrix, incidence matrices. So many of you, I think, are working in graph-related matrices also. So we'll look at some of these. And since you already been introduced to a bit of programming, we'll do that as well. We'll use programming along with these graph-related library functions to do new computations, right? So some of you are working on different kinds of indices associated with graphs. So we'll also see how to compute some of them, which are not already defined in Sage. Okay. So first of all, let's look at graphs. Matrices associated with graphs. So let me take, as you know, a random matrix. Okay. A random graph. In order to see what is happening, I'll take a smaller, maybe 6 vertices. So this is a one particular graph on 6 vertices. It happens to be disconnected. Anyway, what we are interested in, we will change this and see what happens. So what we are interested in is the adjacency matrix of this graph, Laplacian matrix of this graph, and so on. So how do we define the adjacency matrix? Yes, the rows and columns are indexed by. So if you have Aij is equal to 1 if Vi is adjacent to Vj and 0 otherwise. Okay. Right. So yeah, it's a matrix A and C. Yeah, I'll write A of G to denote adjacency matrix of a graph G, and in particular, let's call it A, A1, A2, etc. as per requirement. So here, we are not going to manually define this, although we can do that. You know, right now, you know enough programming to be able to do that because you know how to get vertices of a graph, edges of a graph, and so on, right? By the way, how do you check whether two particular vertices are adjacent in a graph G? I mean, in Sage, if you have G defined in Sage, how do we check whether two vertices are adjacent? Yes. Okay, one is neighborhood set you can take. So neighbors of one vertex, if you ask, you will get that. Okay. So here only 0 is there in the neighborhood of 3. Only 1, right? Otherwise, yes. Distance is 1. That's also one indirect way, right? You can ask for G dot distance between, say, 1 and 2. Is it 1 or not? Right. So in fact, if you write like this, you'll get true or false. Yes, good. So that's one way to see whether they are adjacent. Is there any built-in method? So you can ask, I think has edge, I think, not is edge. Yes. So another way is G dot has underscore edge 1, 2. Okay. So you can extract the list of edges and then check whether something is there in that. That's also a very indirect way, right? You can do something like this 1, 2 in G dot edges. But the problem is their order might matter. Okay. It's not the thing. 1, 2, let me see. It's wrong here. Oh, right. This is not a good way at all. Okay, this way. 1, 2, none in G dot edges, which is unnecessarily complicated. So the simplest way is G dot has edge 1, 2, or G dot distance UV is equal to 1, or anything like that, right? G dot. You can also check. So another one is using neighborhoods. If you directly want to check, instead of looking at the list and saying, you can say 2 in G dot neighbors. So remember to use American spelling because software. So 2 in G dot neighbors of 1, right? That's the same thing, right? So all these different ways are there. So we could now, with your knowledge of programming, you could write a small function to construct the adjacency matrix of G. But of course, it's not really needed because Sage already has it. So we'll just, okay, maybe I'll, it's here, right? So what you can do is A equal to G dot adjacency matrix. That is the adjacency matrix of G. Okay. You can verify. From the adjacency matrix, you can see that vertex 0. The first row here is 0, right? Because the vertices start from 0 in the default construction. So for first row, that is vertex 0, 0 is adjacent only to 0, 1, 2, 3. And the fourth entry is corresponding to, or fourth column is corresponding to vertex 3, because again, you start from 0. Row 1, I mean, row 2, that represents vertex 1. That's, you can see the neighbors are the third and sixth vertices, which is actually 2 and 5. Right? So on. So this is the adjacency matrix. You can also ask instead for matrix of G, I think. Yes. Matrix of G also gives the same thing. Instead of G dot adjacency matrix, you can just ask matrix of G. So that in turn leads us to another way of defining a graph. So yesterday we saw how to define graphs either using adjacency list representation, where you give vertices and their neighbors, each vertex with its list of neighbors. Okay. Another way was you take any standard graph which is already defined and then modify it according to your need. You can add and remove edges as you want, right? So that's one more way. One more way is if you already have the matrix, then you can just ask for the graph of that matrix. So let me define a matrix here. Let's say A2 is equal to, okay. A2 is equal to matrix of. So let's have a small graph. Let's say 0, 0, 1, 1, 1. Yes. So this is which graph? Star graph on 4 vertices. So if I now ask for graph of A2. Oh, wait, I didn't evaluate this cell, I think. Yes. So if you have the matrix, it's not a convenient way of defining it if you're manually writing the matrix, but if you get the matrix from somewhere, then you want that graph for which this is the adjacency matrix. just use graph function again. Graph of the matrix. Huh? Self loop you will get only if you explicitly allow loops. So that's another thing. If you say in the graph construction, if you say allow loops, I think allow loops. I have to remember what's the correct parameter. Okay. If you use this, so let's say, so right now what I'll do is I'll make this entry 1. Okay. And then try to run this. Yeah. So here you are automatically getting it. But there are cases where you get an error. If you don't intend the loop to be there, or by mistake, if you, in some cases. So where that is, if you try to add an edge, if you have a graph without loops, and you try to add an edge between a vertex and itself, it will complain that loops are not allowed. So then you can make it allowed by using that allow loops equal to true. Okay. So I'll show you that also. Let's say h is equal to, so here, yeah, it is automatically taken. I have not tried this before, as far as I remember. So h is equal to, let's say I will start with t graph and then add, or yeah, can. Right now, it's just a totally disconnected graph. Now I'll try to add an edge from 1 to itself. So then it gives me an error, right? Cannot add edge from 1 to 1 in a graph without loops. So if I want to have loops, why that is, I think, self loops. There is a parameter. I have to remember what it is though. Loops equal to 2. Yeah, not allow loops, just loops. Loops is equal to 2. Yes. Now if I add edge, it is allowed. Yeah, but when you're doing it from a matrix, it's not required. It automatically does the correct thing. Okay, so going back to the matrix, is it fine? Can I proceed to the next thing? You all caught up till here, right? Fine. So going back to this graph, and let's look at some more graphs. All right. If I have 3 edges, then of course it's going to be disconnected. That's how it is. Right. So you can see that the matrix changes accordingly. Again, using interact widget, you can generate many graphs and look at its adjacency matrix. You look at the adjacency matrices. Okay, so okay, now we'll do a little bit of theory also. So what do you know? What information can be obtained from the adjacency matrix? Technically, you can obtain all information from the adjacency matrix because it completely represents the graph. faithfully represents the graph. So corresponding to a graph, there is up to reordering of rows and columns, there is a unique adjacency matrix, right? Corresponding to a unique graph, right? Each graph. But what information can you easily get from the adjacency matrix besides adjacency, which is, of course, by definition, it is adjacency matrix. If you don't get adjacency, then it's meaningless. So by definition, you get adjacency from the adjacency matrix, right? You can look at the row I and column J, and if the entry is 1, then the vertices are adjacent. If it's 0, they are not adjacent. Okay, what else? What else can you get? Degree. What are the degrees? How do you get the degrees? The row sums are column sums. Okay. So if you do, how do you get row sums and column sums? Yeah. Yeah, you can write a loop for that, or else you can do, okay, let's see whether sum works. Sum also works. So if you do sum of a list, we have seen that yesterday. If you do sum of, let's say 1, 2, 3, okay, you get the sum of those entries. But if you do sum of a matrix, it'll give you, I guess it gives you the columns of this. Can't tell because here the symmetric matrix, right? Yeah, it should give you row sums, but looks, because I'm not sure whether it's giving you column sums or row sums. Anyhow, that's one way. Mathematically, how do you get this instead of this? Any other way? If you multiply A by anything, all ones vector, right? So you can multiply it by I guess, yeah, I have to give vector, right? Actually, there is probably a function to directly give the all ones vector also. Okay. This is one way. Yeah, in this case, row and column sum will be same because it's a symmetric matrix. So I'm not sure what the sum function gives, whether it in general gives row sums or, so if I take yeah, so by default it gives column sums. Okay, by default the sum function will give you column sums. Okay, what else? What else can you get from the adjacency matrix? So if you take powers of an adjacency matrix, what does it give? Number of walks of a particular length. So the ij entry of a power m is the number of walks of length m from vi to vj, correct? Yeah, in G, that's all understood. Like we already have defined the graph and so on, so I'll not repeat that. So if you take a square, this is a square. Again, let me see. Let me show G for reference. What is the number of walks from vertex 0 to vertex 5? Number of walks of length 2 from vertex 0 to vertex 5. You can see 0, 4, 3, 0, 1, 5, 0, 2, 5. Huh? So, yeah, 0, 4, 3 is not. That's what I was wondering why the entry is not matching. Yeah, my mistake. 0, 4, 3 is, of course, not from 0 to 5. 0, 1, 5 and 0 to 5. These are the only two walks of length 2 from 0 to 5. Therefore, the 0, 5 entry. So here also, because the vertices are going from 0 to n minus 1, and Python indexing is also from 0 to n minus 1. So we can conveniently say 0, 5 entry is indeed 2. Whereas say 0, 1 entry, right? This entry, or normally we call it the A12. Right? So A12 is 1 because from 0 to 1, there is only one walk of length 2, that is 0 to 1. So if you go 0, 4 or 0, yeah, there's no other walk of length 2 from 0 to 1, right? And the diagonal entries are degrees, because the walk of length 2 from Vi to Vi is basically going to one neighbor and coming back. So it just counts how many neighbors there are, which is the degree of the vertex. Okay. Similarly, you can do a cube. So it will give you the number of walks of length 3, right? And so on. Let's look at a larger graph, then I'll point out some. So we'll take a tree, order 8. So by the way, if you have defined a random graph, then you want to study several things on that particular random graph. Like if you generated one random graph, now you want to look at its adjacency matrix, degrees, and so on. Write it in different cells and evaluate, or at least write it in one other cell. Because if you write it in the same cell and evaluate, each time you evaluate, the graph is generated again. So you get a different graph. So if I want to keep it fixed, right, I should not evaluate this cell, which says currently it says in 49, input cell 49. I should not evaluate it again because then the graph will change. So that cell I will leave alone. Okay, this one I can evaluate any number of times. It doesn't matter. This one I should not evaluate again for now because I want to fix this graph and then study it. Although it was initially randomly generated. Okay, now what is the diameter of G? 5. Radius of G. Maybe I'll print it here itself. The diameter is 5 and radius is 3. Okay, so what can you say about walks of different lengths between vertices? If I take only one because it's a tree, right? Get only one because it's a tree. Sorry, I did not define the adjacency matrix. This is the old one. Right. Yeah, this is a square, a cube, a power 4. So this is the graph of order 8, in particular a tree of order 8. No, the number of walks will not be 1 or 0. Because number of paths, there is a unique path between every two vertices, but not a unique walk, because walk means what you're allowed to repeat, right? So you can go to a vertex, come back, go to another vertex, come back, and then go to the other vertex. Even that is allowed. So number of walks will not be 1 or 0. Okay. Number of paths will be. Anyhow, if I take a square, a cube, so on, a power 4. Can you tell me anything about this? Something guarantee. Okay, even identity matrix, if I take, I'll call it. Anything noticeable? Okay, let's see. Suppose I add all of them together. Huh? Anything you know about this? Even that the diameter is 5, what can you say about it? Diameter of the graph is 5. So if I take I plus a square plus a cube plus a power 4, or even I can write whatever constants I want here, any linear combination of I, a square, a cube, and a power 4, what will it have? Can I say that one entry will definitely be 0? At least one entry will definitely be 0. Here you can see that it is. No matter what constants I take and multiply and add, whatever linear combination I take of these matrices, I, a square, a cube, a power 4. At least one entry is always 0. Why? Huh? That's not. There is one path of length 5, yes, but so what? Something stronger. But we have not gone to higher powers. We have not gone to a power 6 or so on. And in fact, we don't need path. We want walk. So we can have walks. Yes. That is the point. There is no walk of length less than 5. There is a path of length 5 is not the thing. There is a shortest path of length 5. Because diameter is 5. Diameter is 5 means maximum possible distance 5. Not only that, between two particular vertices, the distance is exactly 5. You know that, right? Since the distance is exactly 5, any path between them will have length at least, any walk between them will have a length at least 5. You cannot have a shorter walk. Because a shorter walk means there is a shorter path also. Then the distance would not be 5, it would be smaller, right? So you cannot have a walk of length less than 5 between, for example, these two vertices, right? This is what vertex 5 and vertex 4 and vertex 1, right? Vertex 0, right? 0 to 4, if you see, 0 to 4, 1, 2, 3, 4, 5. Distance is 5. There is no walk of length smaller than that. So whatever powers you take up to 4, this entry will be 0 in all of them. Because there is no walk of length 0, 1, 2, 3, 4 between these two vertices, right? So therefore, this entry will always remain 0. In fact, that is also true for, so if there are vertices at distance 5, then there are also two vertices at distance 4. So in that, between those two vertices, that ij entry will be 0 for I, a square and a cube. Similarly, you will get distance 3. So in 0, I mean, I, a square to one particular entry will be 0 and so on, right? So for every such power up to 5, up less than 5, you can find one entry which will definitely be 0. So using this, you can reason out, it's not too complicated. You can reason out that all these matrices will be linearly independent. If you take I, a square, a cube, and a power 4, these will be linearly independent because each of them has a 0 in at least one spot, right? Which, not in that way. All of them have zeros in one particular place at least, right? Which won't be there in the higher power. Because if you go to the higher power, you will have a path of that particular length. So if I take a power 5, will this entry still be 0? Other zeros may be there, but this entry is not 0, correct? So this entry, this 4-0 entry or 5-1 entry, whatever convention you follow, right? This entry is not 0 in a power 5, but it is 0 in all these matrices, which means a power 5 cannot be written as a linear combination of I, a square, a cube, a power 4. Similarly, a power 4 cannot be written as a linear combination of I, a square, a cube, and of course, a power 5 also, and so on, right? So if you take all these, they will all be linearly independent, which means together, I, a square, a cube, a power 4, a power 5. This is a linearly independent set of matrices, right? But what further thing does that tell you? So I'll summarize what we have seen in this particular example. If diameter of G is equal to K. If diameter of G is equal to K, then and A is equal to AFG, then these are all linearly independent. Okay. That is what we are seeing. You can go through the reasoning again later. But what does that tell you? What useful fact does that tell you? Can you say anything about eigenvalues based on this? So, for example, how do you know how many distinct eigenvalues a matrix will have? Yes. How many independent eigenvectors are there? Yeah, that is geometric multiplicity. So there are, that is for a particular eigenvalue, how many times it will occur. Okay. That will give you the geometric multiplicity, the number of independent eigenvectors for a corresponding one. But okay, what are the polynomials associated with the matrix that help you find the eigenvalues? One is a characteristic polynomial. Okay, let's look at that. This is a characteristic polynomial. Okay. It gives you that. In fact, if you give show of this, then give you a better version. Any other polynomial? No, related to eigenvalues. Minimal polynomial. For any matrix, not particularly for graphs, for any matrix. I should have made that. Right. Minimal polynomial. Here, the minimal polynomial happens to be equal to characteristic polynomial, which in fact indicates that. Sorry? All eigenvalues are distinct. Yeah. Here, all eigenvalues are distinct. Okay. What it is? Yeah, A is a Disney matrix of a tree. But even then, you can have repeated eigenvalues. So, for example, I'll show you. Yeah, star graph is one simple case. I'll pick B. Oh, I'm not evaluated, so I can't. This is one example where you have many repeated eigenvalues because star graph has 0 as eigenvalue. The rank of the adjacency matrix of star graph is rank. Rank will be 2. Yeah, nullity is n minus 2. Rank is 2 because first row will be 0, 1, 1, 1, etc. Second row will be 1, 0, 0, 0, etc. These are obviously independent, but all the other rows are also 1, 0, 0, etc. Right? If you take the central vertex as the first vertex, then this will be right. So multiplicity, number of distinct eigenvalues is just 3, just 3, right? What are the eigenvalues? 0, n minus 1. Yeah, square root of n minus, yeah, plus or minus square root of n minus. So that actually for complete bipartite, maybe we'll see all those examples. Complete bipartite graph with P and Q as the cardinalities of the partite sets, 0 and plus or minus root PQ. These are the eigenvalues, right? So here there are 3 distinct eigenvalues. The characteristic polynomial has degree 3. Huh? Sorry, minimal polynomial has degree 3. Okay. So yeah, so coming back to this. If you know that I, a square, etc., a power k minus 1 are linearly independent, what does that tell you about characteristic polynomial? By the way, what is the characteristic polynomial definition? Sorry, what is the minimal polynomial? Yes, it is an annihilating polynomial with characteristic polynomial is also an annihilating polynomial of the matrix, but minimal polynomial is the minimum degree unique monic polynomial with of minimum degree which annihilates the matrix, right? For any matrix, any square matrix. So if you have I etc. I a square etc. a power k minus 1 are linearly independent, that means what? No polynomial of degree k minus 1 or smaller can annihilate A, right? No polynomial, because polynomial, suppose you have a polynomial of this form, p of x equal to some a naught plus or some c naught plus c1x plus c k minus 1 square k minus 1, right? Suppose this is your polynomial, then p of a is c naught plus c1a plus c naught I. Right. So if you take a polynomial of this form where ck minus 1 may be 0 also, right? So this is a polynomial of degree less than or equal to k minus 1. Can it annihilate A? Annihilate A means this linear combination should be 0 for some ci, right? Some ci's, this linear combination should be 0. That is not possible, right? Because there is no such polynomial of degree. I mean, of course, all CEI have to be 0. That is, again, that cannot be minimal polynomial. 0 cannot be minimal polynomial. So that is not possible, right? Because these are linearly independent. So that tells you that the minimal polynomial has degree at least k. So that means number of distinct eigenvalues is at least k. So if the diameter of a graph is k, the adjacency matrix is at least k distinct eigenvalues. That is one thing immediately that you can get from the this information, like from the knowing the eigenvalues, you can say the diameter is at least this much, right? So when you study these parameters, like you take the matrix of the graph, that is okay because it represents the graph, but then you study matrix parameters, right? Matrix properties. So you have many things defined in linear algebra or matrix theory, but you are studying graph theory. So what is the point of saying that this matrix has this eigenvalue, this many eigenvalues, this is the what is it, largest eigenvalue and so on. So there should be something that you know about the graph from that. Otherwise, it's pointless. You can just say that, but it doesn't really become study of graph theory. So point is, whatever you find there, you have to relate back to graph theory, right? So this is one of the things, one of the most elementary things. The number of distinct eigenvalues tells you, gives you a bound for the diameter, right? Knowing the diameter, you can get the bound for number of distinct eigenvalues. But more interesting thing is if you find the number of distinct eigenvalues, you get a bound for the diameter. Okay, so that is one thing. So now to look at some programming thing. Suppose you think this is correct, right? Maybe you form this as a conjecture by looking at many examples, or you reason this out theoretically, but you're not really sure of your reasoning. So how do you test it? One way is, as I said, interact. You can write the interact widget and then change the values and see, right? Test it, or you can write a loop because you know loops now. So let's take something like for let's say n is equal to some reasonable number. So 2 to 1, there is no point, right? 2 even 2 also is sorry, I'm using another notation. So n in range of, how do you specify a range? Which does not start from 0, you give the initial value. So let's say I want to start from 3 and go up to order, let's say 10 for now. Okay, so I'll give 11. You can just write 11. I want to emphasize. The point is, if you give range of I comma j, it will give you I plus 1, etc., j minus 1. Okay. So if you want 10, including 10, you have to give 11. We keep it simple for now, and then we'll make it better and more complicated. Right. So we'll take start. So right now I just check for trees. Okay. Random tree of order, and then we'll progressively complicate it. So when you, in general, when you write code also, that's what you should do. You should not think of the most complicated version and then write it in a linear manner from first line to last line. Build it up logically, right? So logically, what is the smallest part of that that can be independently done? That you do first, and then add to it, right? Because if you write a big block of code and then run it, and then there is an error, you won't know where is the error. Okay. So do the simplest thing possible, then add to it. Right? Okay, so this, of course, this works, right? I'm just showing trees. I'm just generating random trees of different orders and showing them, nothing else. So actually, I don't want to see the tree. I want to just get the value of the diameter. Right? Yeah, sure. It does this. If I run this again, I might get slightly different values. Of course, the diameter will in general tend to increase because I'm going for larger and larger trees. There is always a possibility. Yeah, here you can see that diameter is become 5 here, then 4, then 5. Because you can always get a star, right? Technically, it's possible that the last tree has diameter 1, not 1, 2, because it's a star. Okay, so I can do this much. Now, what do we really want to check? The relation between degree of minimal polynomial and diameter, right? Or number of distinct eigenvalues and diameter. So I will ask for the adjacency matrix of G, then take its minimal polynomial. So uh, just call it mx. Hopefully, I should be able to find the degree. Yes. So what is our conjecture or theorem really? But since we are not really written down the proof, we call it a conjecture. What is a conjecture? Diameter is less than or equal. So I'll actually print that as well. Yes, in all these cases, it's true. Can, of course, easily go to larger values. But this is only for trees. So you should change it to some random graphs. But then if you take a random graph, it may not be connected. That is also a problem, right? So what can you do? If connected, you can give if connected. Is there a way to generate connected graph? I think there is one. Maybe not. So there are different ways to do this. One way is to, because it's more or less guaranteed that if you give a reasonably good probability of generation of edge or number of edges, you will eventually get connected graph if you keep generating random graphs. So you can write a while loop inside this for loop, which will just run it until you get a connected graph. That'll make it slower. So one thing you can do is take a random tree to begin with, because that is minimum requirement for connected graph, and then add some edges randomly. Okay. So how to do that? Yes. Eulerian Hamiltonian. That is also not there. Okay, let's see what is there. Random bipartite is there. Regular, etc. But they don't, none of these will guarantee connectedness. There are different ways of solving this problem. Okay. I'll try it like this. So okay, it's still true, but you have to tell me what I did. What have I done? So what I added is this. These two lines are what I added. What? Louder. Huh? No, no. What is he? You can speak louder. Umesh, what is she saying? I can't understand. Is that the question? Hmm. You can do it. N double slash 3. What is that? Let's see. 100 double slash 20 is 5. 100 double slash 25 is 4. 100 double slash 26 will be integer division. It will take floor of the this one so that I get an integer. I can't give floating point number of edges. So it is a integer division. Okay. Very useful tool. I mean, you can always do floor of n by 3. It's simpler. This is Python, not Sage. Double slash is Python syntax. Okay, so I have taken random number of edges. I mean, not random number of edges, n by 3 edges, generated a random graph with that. But I know that because both of these graphs are generated automatically, the vertices will be from 0 to n minus 1. So the vertex labels happen to be the same. So I have generated another random graph, but with n by 3 edges, right? Floor of n by 3 edges, and then taken those edges and added to G. G is already a tree, so it's connected. Now, if I add any more edges, it is not going to become disconnected. I will randomly add some edges. Because the limitation is the number of edges is fixed, right? I can instead give probability. Random G and P can be given. No, because when you randomly generate, it will not give this. So this is one question. If edges, suppose the edges are repeated. Like suppose H also has the same edges G already has. Then no problem. It will not consider it as a multigraph because we have not defined it as a multigraph. It's by default a simple graph. So when you add an edge which is already there, first of all, for the purpose of diameter, it doesn't matter at all. But of course, the adjacency matrix will be different if you consider multigraph. But the point is, it will not consider it as a multigraph. If you try to add an edge which is already there, it will just ignore it. That is the thing. Okay. Yeah. That's a relevant question. So it will ignore edges which are already there when you try to add. Okay, I can instead use probability. So if I want a small number, then instead of n by 3, I could give 0.33 or something. 0.3 I'll give. Just adding a small number of edges, not large. You can always try adding larger number of edges. Why I'm adding small number of edges is because I don't want the diameter to go down too much. Right. Here, even then, the diameter is quite small. Maybe I'll add very few edges. Yeah, so then you get a nice variety. Right? You can see that the bound is not a very good bound in many cases because the degree of the minimal polynomial is very large. There's many distinct eigenvalues may be there. Right. So it's not a great bound, but it's true. Okay. I mean, it's most probably true. You can actually write down the proof, so it is in fact. Okay, what else? This is the adjacency matrix, adjacency eigenvalue. Also, there is another thing. What we did right now is get the adjacency matrix and then get its eigenvalues. Actually, we didn't see the eigenvalues at all, right? So for eigenvalues, you know already. You can ask for the eigenvalues. So it will show you. So this is now the order 50 graph. So I'll go back to our earlier graph, which is now going to be changed. Go back to this order 6 graph. No, sorry, you missed it. I have changed the code here and made it up to 51. The order of the graph is now up to 51. Yeah. Okay, so here's a graph. I don't know if it's called a kite graph. Anyway, it looks like a kite. Possibly it is, right? So there is a kite graph, but I don't remember what to the shape. Right. So these are the eigenvalues. This is one way, but you don't really need to get the adjacency matrix and then get the graph. What is the set of eigenvalues called? Multi-set of eigenvalues is called spectrum. That's it. You can just ask for the spectrum and it will give the standard ordering, non-decreasing order, non-increasing order. Okay. So if you directly ask for the spectrum of a graph, you don't need to generate the matrix first. It'll give you that. But it's going to give you the numerical approximations because in general, there is no way to get the exact eigenvalues. Right? There are only numerical ways to solve this. Because if you know that if you have a polynomial of degree 5 or more, what is the thing? Any polynomial of degree 5 or more, there is no general way to solve it in terms of radicals. Right? Galois theory tells you that. In general, there is no, like quadratic equation, you have a very nice formula. Minus b plus or minus b square root of b square minus 4ac by 2a will give you the roots. Cubic also, there is a formula, although it's complicated. Quartic equations with degree 4 equations. They also have a very complicated formula. But from degree 5 onwards and higher, there is no general formula that will give you the roots of a polynomial equation, right? Degree 5 or more. So you have to resort to numerical methods. So if you ask for eigenvalues of a matrix or a graph, you will get the numerical approximations. In certain cases, you may get the exact ones, but in general, no. Of course, you can always get the characteristic polynomial. That is it. Characteristic polynomial, you can get the nice one, right? And adjacency matrix has many nice properties when you think in terms of eigenvalues. One is that it's a real symmetric matrix. So it has real eigenvalues and it is diagonalizable, orthogonally diagonalizable, in fact, right? Which also means that the geometric multiplicities and algebraic multiplicities of all the eigenvalues are the same. Like for each eigenvalue, geometric multiplicity is equal to algebraic multiplicity, right? So all these things are there. It's the nice properties of adjacency matrix. So you can get spectrum of G using this. So again, relating to what we saw earlier, if you do so actually, let me show you the map function. Okay. Or maybe I'll show a simpler method. Okay, suppose you have a list of elements. I'll just take an example. Okay. Consider this list. We'll go back to graphs in a moment. Consider this list of elements. I want to square all the elements of the list. What is the way that you know how to do it? Yes, loop. So currently what you know is you can write a loop, take elements from this, right? And then, for example, you could print the square. By the way, if you are using Python rather than Sage Math, don't use this operator. You have to use star star. Okay, that is one thing. In Python, the power operator is star, double star. Okay, but Sage Math nicely allows you to use the more familiar one, which is this. Okay, this is one way. This is printing it. I don't want to print it. I want to get a list. One way is you can write something like empty list, then y dot append x square, and then you can see y. So this is one way. This is quite tedious. I'm writing 4 lines for this. Any simpler way? Yes. Dot operators in MATLAB. MATLAB has a dot operator where you could just do access dot. Don't write this. It's not Python. It's not going to work because it's MATLAB. In MATLAB, you can do this. Anything equivalent? List comprehension. So what we have is list comprehension where, so remember in mathematics, how would you write this? Suppose X is a set of elements. I want to write Y is equal to set of squares of elements of X. How do you write this? Yeah, you will write X square for X in X, right? This is how you would write it in mathematically. Same thing you can do in Python. Y, I'll not name it. I'll just write X square for X in X's. Okay, this is called a list comprehension. Very often you don't want to name it as a new list or anything. You just want that list to use once. So you don't have to write Y and then add elements to Y and then use it. You can just use it in place. So for example, if I want, now how will you write? In one line, you would write sum of squares of elements of X, elements of X's. X's is a list. You can think of it as plural, X's. Many X's are there. So I want sum of the squares of the elements in this list X's. How do you get it? In one line. Sum. And then this, right? X square for X in X's. That gives you. Okay. So now what I'll do is, going back to the graph, I have G dot spectrum. What will be the sum of G dot spectrum? No. 0. Because sum of the eigenvalues is trace of the matrix. Trace of edges in the matrix is 0. Because of numerical approximation, you can see that it's only approximately 0. It's 0 times 10 to the power of minus 18. 0.0000. So many. Then 1, right? So, but it's close to 0. That's fine. Close enough. So if you want sum of squares of eigenvalues, then so you consider this is a list. G dot spectrum is a list. So X square for X in G dot spectrum. What is this? Why is it an integer? Because you had so many. Yeah, this is twice the number of edges because it's trace of A square. Remember that A square has as its diagonal entries the degrees of the vertices, and sum of the degrees is, as we saw yesterday, it is twice the size of the graph. So this is always going to be twice the number of edges. Okay, so this is another information that you can easily get from the adjacency matrix, even from the eigenvalues, right? What if you take cube? 6 times number of triangles. Okay, so G dot number of triangles. I can't get. That's not good. Yes. So that luckily is a function G dot triangles count. There are 4 triangles, and this is indeed 6 times number of triangles in G. Yeah, how to get the energy? Sum of ABS. So instead of x cube, if you do ABS, this is the energy. Okay. So I don't think energy is function. I mean, it's not a library function, but this is an easy way to get the energy, right? Even for the matrix, no. Energy is not already defined, but it's just one line. Not difficult. You can easily define it, right? So let's define energy for a graph itself, right? So how do you write this function? You want to return sum of, so from G dot spectrum, ABS of eigenvalues, right? You can even write, okay, don't write lambda. Don't write lambda, I'll tell you why. Lambda is a keyword in Python. But maybe I will explain its use later. It'll be too confusing now, unless you're familiar with it already. So this is going to give you energy of G. Okay. Now, if you have different kinds of energy, you can also define that. Means if you have defined some variant of this, that can also be defined. Right? Okay, what other matrices are there? Laplacian. So you can get the Laplacian matrix as well, which is just the diagonal matrix of degrees minus the adjacency matrix. So you can see that along the diagonal, the degrees of the vertices are there. And then the ij entry other than the non-diagonal ij entry is -1 if and only if vi is adjacent to vj, 0 otherwise. Right. That is the Laplacian matrix. Again, you can take the Laplacian matrix and then get its spectrum, or else you can directly ask for spectrum, but with this optional parameter set to true. So if you say, again, G dot spectrum, Laplacian equal to true, it will give you the Laplacian spectrum rather than the adjacency spectrum. Okay. Here 0 happens to be an eigenvalue. Is it happens to be eigenvalue, or if I change the graph, maybe it won't be? Huh? Yeah, it will. 0 is always an eigenvalue of the Laplacian matrix. Not only that, the multiplicity of 0 as an eigenvalue of Laplacian matrix gives you the number of connected components. So the graph is connected if and only if 0 is a simple eigenvalue of the Laplacian matrix of G. Okay, so I'll just give the definition of Laplacian matrix. Yeah, so one question is it possible to create a question from online participant? Is it possible to create code for a newly defined domination parameter to find the new domination number? Yes, definitely. You can write, like as we saw, very simple cases already. So we'll look at more complicated examples also, where we have some parameters defined, and then you can, if it is defined in terms of the graph, obviously, you can write the code for it, right? And write it as a function so that whatever graph you give, it will give you the value of the parameter for that particular graph. Okay. We will see examples. Okay, let me see. So again, assume that n is already a graph defined with vertices v1 to vn. Not repeating that. Right. So yes. Huh. Multiplicity. Huh? Let me see. First of all, possibly there's no direct code, I guess. Okay, I can't find a standard function, so we'll define one. Okay, that's a good problem. Suppose I have a large matrix, like order 50 or more. I want to count the multiplicity of a particular eigenvalue, and it's not a good thing to sit and count it, right? There is a good chance of error, and of course it's tedious, and you might also want to automate it because you want to test it for many cases. How do we automate this? So the basic problem is nothing to do with eigenvalues. It is in the list. How do you count number of elements of a particular value, right? Um, right. So let's try that as a programming problem. So I have some list. Okay. So maybe I'll take a particular list so that I know how many elements are there of each particular value. Okay. Three. I'm not going to be very, like, I don't need 1, 20, 30, and so on. The point is, I know that this many ones, twos, threes, fours, or fives are there. The particular values also don't matter, only the multiplicities. Okay, maybe let's 6 also. So I have 1 occurring once, 2 occurring 3 times, 3 occurring twice, 4 occurring, I don't know how many times, then 5 and 6 occurring once each, right? Now I want to count these multiplicities. So what is the best? Huh? Yeah, sorting you can do easily, right? So even if the list was not sorted, if I give x of x's dot sort, now it is sorted. So if I had not sorted, so suppose I had inserted some 4 here and 6, let's say 7 here. Okay, so it is still sorted. So sorting I can do. That's correct. Huh? Comparing I and I plus 1, right? So when it changes. So that's what I'm thinking of. What is the simplest, not necessarily simplest, but shortest way of doing it, which may not be that simple. Okay, so let's try to do it the more obvious way. Something should happen if you have, in fact, I should go up to this -1 only. Yeah. If it changes, then I should do something to the count. So, okay, how, as a general principle, when you're trying to write some program like this, at least to begin with, when you're writing the simplest version of it, let's say, you should think of how you would do it manually and then translate it into code. So, how would you do it? You are seeing this list. It is guaranteed that it's sorted. I've already sorted it. Okay. So, first step of this would be sort. Okay. So now I know that it's sorted. Now that it's sorted, how do you see when you go through the list or scan through the list one by one? How do you actually count the multiplicity? So this is 1, 2, and then you stop because it changes. So when it changes, you stop counting, and then you start counting for the next one, right? So then you say 1, 2, 3, and then stop, right? So what I'll do is, so do you want just the multiplicities or multiplicities together with the value? Okay, let's say multiplicities together with the values. Okay, so this stands for VMs, that is values multiplicities. I'm just using that convention, just that internal definition I'm using. So I will create a list of ordered pairs of value comma multiplicity. Fine. This is a standard, somewhat standard representation for a multiset, where you have, what is a multiset? You have a list of ordered pairs. In one definition is a list of ordered pairs, which is one value, comma, its multiplicity in the set. Right. So in a normal set, there is no repetition of elements. In a multi-set, you can have an element any number of times. Right. So multi-set representation, one of the common representations is ordered set of ordered pairs. First component tells you value of the element. Second component tells you the multiple. So I will follow the same. So I start with an empty list. And then, yeah. So whenever the value changes, then I will add it, okay, as an ordered pair. So append what? Ordered pair. I'll show you the thing. I'm adding an ordered pair, which is the current value, which is excess of I, comma, its multiplicity. But what is its multiplicity? So that I have to count. So here something like count equal to, or let me just say m. M is equal to 0. Actually, I should start from 1, right? Whatever I'm counting, at least 1 is there. Otherwise, I'm not counting it. Uh, inside loop, sorry, outside loop to begin with. So when the value changes, what do I do? Then I reset it, right? Otherwise, what do I do? Increase, increase it, right? Each time, should I increase it beginning or afterwards? No, here I should increase it. If the value does not change if the next value is the same as current value, increase the multiplicity, right? If the next value is different from the current value, add the current value, comma, current value of multiplicity to the list. Okay. Huh? No, because at least one element is there. Meaning, at least once that element is there. If the list itself is empty, then this won't run at all. So VMs also will be 0. Right? But as soon as I start counting from 1. Let's see if it works. Yes, seems to be working, correct? So you can now write this as a function. in place. So there are two functions for sorting. One is access dot sort, which changes the list itself. If I want the sorted list without changing the original list, then I can use access dot sorted. So for example, if I give, say now, for example, if I give oh wait, sorted of X, sorry, not access dot sorted. Hold on, hold on. Yes. So this does not change the original list. Okay. Whereas if I do want to change it, then I will give access dot sort. And access dot sort does not give you any value. So if I print access dot sorted, sorry, access dot sort, what do you think it will print? Oh, yeah, yeah. 7 is not counted. Yes. 7 is not counted because, oh, correct. That is right. Yeah, yeah, yeah. 7, correct. Is this a corner case or meaning do I need to make two cases to deal with this or? Yeah. One or the other will be an exceptional case, right? There's no uniform way of doing it. If it changes, then maybe. Let's see. And then no, the problem, the reason I need to do this is because I'm going to excess of I plus 1. So then I should start from 1. So I should start from I equal to 1. The M is not the problem. I is the problem, right? -1. No, I have to. Yeah, so it does cause an error. Yeah, so let me think. Logically, what should it be? When I actually look at this list, when I actually look at this list, if I say 1, 2, and 1, 2, 3, 1, 2, etc., etc., 1, 6. Yeah, I have to write an exceptional case here. Okay. So, okay, there is also a question. Sandeep is not there. Did you do Boolean operators? So, Boolean operators. So, either I is strictly less than length of access -1. Then I can do this. Or else, okay, this else I will keep as it is. Remember, the index is anyway going to be 1 less than the length for the last element. Huh? Ah, yeah, elif. Sorry, not else. Elif. Elif this. In that case, again, there are two possibilities. Suppose this was 6 and 6. Then I've already counted it. If it is not, then I need to. So elif this and now minus 1. Right? Now excess of I equal to or not equal to. Not equal to excess of I minus 1. Otherwise, don't do anything. Right? Yes. So this works because when you reach the last element, either it has already been added. But if it has been added, then the previous element is the same. So then I don't do anything. Right? If it has already been added, don't do anything. If it has not been added, that means they are not equal. Then I add it. Right? So suppose I change this 7 to 6. Then this should change also. Right? Oh, no. Right. So one more case is, or I need to write it internally. Wait, how come? Oh, yes, I understand. No. The problem is it has not yet been added. So, no. Yeah, 9 plus 1. Why should it be? No, because this is the last element. No, it has no. This is the last element. Len of x is minus 1 is the index of the last element already. It is not index of second last. It is index of last element. But the thing is, yeah, I understood the mistake. The last element has not yet been added anyway. Yeah, it is just one exception. It's not two different exceptions. It's just one exceptional case. Last element will not get added until you reach the end of the list. Okay. So when you reach the end of the list, just append the current value of m. Current value or 1 plus value that I will check and yeah, correct. This is correct. This is correct. We'll change it again and check. Add. Yeah, this works for both cases. Okay. This works for both cases. Yes. There are possibly more efficient ways of doing it. I'm not sure. No, but this is actually linear. Yeah, this is linear. Okay, so we'll take a break and resume after 10 minutes, 15 minutes, 15 or 10, 15 minutes. We'll take a 15-minute break now and resume at 3:45.